The operating system is the manager of the machine. It doesn't execute your code. The CPU does that. The operating system organizes, isolates, and supervises. Today, we're going deeper, because that management layer is not just administrative. It is the reason you can reason about software at all. Managers create boundaries, and boundaries make behavior predictable. If nothing enforced separation between programs, you could not trust state, timing, or memory. Isolation is not a convenience feature. It is the foundation of stable thinking in computing. Imagine a system with no operating system enforcing boundaries. Every program shares the same memory. No ownership. No protection. If one program writes to memory, any other program might read or overwrite that same location. The CPU doesn't know which program owns the data. It just executes instructions. Without the manager, everything overlaps. And when everything overlaps, nothing is reliable. Software is not an actor in your system. It never initiates anything. It never reacts. Suppose App A writes a value into memory. It assumes that memory belongs to it. But App B also assumes ownership of the same region. App A updates a number. Suddenly, App B crashes. From App B's perspective, nothing changed. Yet, everything changed. Without isolation, cause and effect disconnect. Without isolation, one program could directly read another's memory. Passwords, tokens, sensitive information. The operating system prevents that by assigning private memory spaces. That privacy isn't optional. It's enforced. Isolation protects integrity. When a program crashes, your entire machine usually doesn't shut down. The failure is contained. That containment exists because the operating system enforces isolation. Each process runs inside its own memory boundary. If something goes wrong, corrupted data, invalid state, unexpected behavior, the damage is limited to that process. The operating system can terminate it and reclaim its memory without affecting everything else. Now imagine no isolation. A faulty write could corrupt another program. A crash could spread. One mistake could destabilize the entire system. Containment turns catastrophic failure into localized failure. And that is what makes modern systems survivable. When something breaks in your program, you don't assume every other application on the machine caused it. You assume the issue lives within your process. That assumption is valid because of isolation. The operating system enforces boundaries around memory and execution. Other programs cannot directly overwrite your working memory. That dramatically shrinks the search space. Without isolation, any failure could originate anywhere. When you know where interference cannot occur, you gain confidence about where to look. Isolation doesn't just prevent interference. It enables measurement, because each process has its own assigned memory and scheduled processor time. The operating system can track exactly how many resources it consumes, how much memory is it using, how much processor time has it received. Those questions only make sense when ownership is defined. Without isolation, memory and time would blur together. No clear responsibility. Tracking enables fairness, and fairness keeps the system stable. Isolation is what turns shared hardware into an organized, measurable environment. Maybe removing boundaries would make systems faster, fewer checks, less management, direct access to everything. But unwanted sharing trades small efficiencies for massive instability. You might think that removing boundaries would make systems faster. Fewer checks, less management, direct access to everything. But unmanaged sharing trades small efficiency gains for massive instability. Without isolation, programs would interfere constantly, failures would spread. The operating system chooses stability over raw speed because stability scales. Isolation introduces structure. Structure introduces overhead. But that overhead buys predictability. Fast chaos is useless. Stable systems win. Your program lives inside a box. That box is not imaginary. It is enforced by the operating system. It defines what your program can see, what it can modify, and what it cannot touch. When you run a program, you are not releasing it into open space. You are placing it inside a managed boundary. Everything it reads and writes must exist inside that boundary. There's no invisible interference or shared chaos. Every application loaded by the operating system follows a life cycle. First, it is loaded into working memory. The operating system assigns it a private region and prepares it for execution. Then it becomes active. The processor executes instructions with boundaries. Eventually, the application exits, either normally or due to failure. When that happens, the operating system removes it and reclaims its memory. Because the operating system manages each stage, the life cycle is predictable. Start, run, exit, reclaim. Without isolation and tracking, memory cleanup would be unreliable. But with boundaries enforced, application lifetimes remain controlled and finite. A browser, background services, system utilities, all loaded into working memory simultaneously. That scale is only possible because the operating system isolates each one. Memory is divided into separate regions. Execution time is scheduled and distributed. Resource usage is tracked. The operating system turns shared hardware into a coordinated environment. Stability at scale is not automatic. It is enforced. The operating system divides memory quietly. It assigns resources silently. It schedules execution invisibly. Every loaded program exists inside structure created by the operating system. The manager may be unseen, but it is always present. Isolation creates predictability. Predictability enables reasoning. And reasoning enables engineering. Without boundaries, software would be guesswork. With boundaries, software becomes structured thought. If a program needs more memory, it requests it from the operating system. The operating system can accept or reject this request. This control expansion prevents one application from consuming all available memory. Isolation is not static. It is actively managed. The operating system supervises growth as well as separation. Without this management, aggressive or faulty programs could dominate the machine. Boundaries are not just walls. They are governed spaces. The operating system is not your executor. The CPU executes instructions. The operating system organizes the environment that makes execution safe and stable. It assigns memory. It enforces isolation. It tracks ownership. It schedules time. Because of that structure, your program can behave predictably. In the next phase, we'll move into scheduling and time. Because once isolation is clear, the next dimension is when execution happens.